This last plot plots the wave impedance on the horizontal axis and the S parameters in decibels in the vertical axis.
A rectangular cavity resonator.
Thank you, this is the end of the presentation.
A cavity resonator is a hollow conductor blocked at both ends and along with an electromagnetic wave can be supported. It can be viewed as a waveguide short-circuited at both ends, just like a microwave cavity. The cavity's interior surfaces reflect a wave of a specific frequency. When a wave that is resonant with the cavity enters, it bounces back and forth within the cavity, with low loss, just like a standing wave. As more wave energy enters the cavity, it combines with and it reinforces the standing wave, increasing its intensity. The structure I chose to implement in OpenEMS was the rectangular cavity resonator. One can create a rectangular resonant cavity for electromagnetic waves by taking a rectangular waveguide and closing off both the two ends of the waveguide. Rectangular waveguide, as opposed to circular and elliptical waveguides, are by far the dominant configuration for the installed base of waveguides for compact systems like radar and inside equipment shelters. That is probably due to the generally greater rigidity of rectangular structures because the wall thickness can be easily made thicker than with circular. It is also easier to route and mount in close quarters, and attaching penetrating objects like probes and switches is much simpler. This is the approach I took in order to implement this structure in OpenEMS. Also, the rectangular cavity is only one of the many cavity devices that are useful as high-frequency resonators. The figure on the left shows the structure of a rectangular waveguide. As you can see, it is open at the front and the back. The figure on the right is the structure of a rectangular cavity resonator. As you can see, the front and back of the rectangular waveguide is just blocked off to get the structure. The reason we close the two ends of the rectangular waveguide to get a rectangular cavity resonator with metallic walls is because the wave propagating in the Z direction will now bounce off the two walls, resulting in a standing wave in the Z direction. The MATLAB code I created to implement the rectangular cavity resonator starts here. This code just introduces and initializes all the dimensions for the box, the stop and start frequency, and the physical constants. I set my waveguide dimensions length to 500 to 5000, the width to 1000, and the height to 1000. I set the starting frequency to 300 times 10 to the negative 6 and the stopping frequency to 500 times 10 to the negative 6. The next part of the MATLAB code here is the first line just creates a vector frequency of 201 linear spaced numbers from f start from the frequency starting and the stopping frequency. The next few lines are initializing the cutoff frequency, the waveguide phase constant, and analytical waveguide impedance. Also, the magnetic field and the electric field are introduced and implemented with the functions from my research with the specific mode I'm implementing. The second half of the code sets up the FTD parameter excitation function boundary conditions. The next part of the code, I set up the CSCAD mesh by creating a smooth mesh between 0 to A, 0 to B, and 0 to negative length. I have to add two copper plates to both ends of the rectangular structure in order for it to work as a rectangular cavity resonator. The next few lines I code the XY mode profile excitation located directly on top of PML, which is the first 8 Z lines. The next part of the code is this. The first half of the code here creates the waveguide ports in my structure, which makes use of the electrical magnetic field functions I introduced earlier. The field dumps define the coordinates where the field is saved during simulation. This is the next part of my code. The first few lines of this code create the directory for simulation use, writes and runs the OpenEMS code. The rest of the code just plots the S parameter in decibels versus the frequency in millihertz. This code compares the analytic and numerical wave impedance of the structure and plots it with the wave impedance on the horizontal axis and the S parameter in decibels in the vertical axis. Also, the second half of the code plots the field dumps. If you run my code, you'll see the field dumps. These are the results obtained from just the time step 0 to 1458. But if you run my MATLAB code, you'll reach time stop 2328 and the results for the graphs will appear. This is the plot of the S parameter in decibels versus the frequency in millihertz. And as you can see, the black line represents S11 and the red line represents S21. This last plot plots the wave impedance on the horizontal axis and the S parameter in decibels in the vertical axis. Thank you. This is the end of the presentation.